see so many folks interested in hearing more about Putah Creek salmon. It's personally one of my favorite conversation topics, and we're really glad to be able to share with you tonight some of the things our group has been doing to monitor and better understand the salmon on Putah Creek. As I said previously, for the past 2 years, I've had the opportunity to join the really great team at UC Davis working on Chinook salmon. This is a long-term monitoring project beginning its 5th year this fall, and a lot of people have contributed to its success, including Gabe. He downplayed how much he helps. But I'll start by thanking the fine group of people who have dedicated so much time to learning about our salmon, especially Peter Moyle, who was instrumental in initiating this long story of returning salmon. I'll also stop now to note that this work is funded and technically supported by the Solano County Water Agency. Okay. Let's start with a little bit of background so that we're all on the same page to appreciate this journey. Prior to 2000, since roughly the 1950s, much of the creek looked like this. And that's for a lot of different reasons, a few being dam construction, impoundments, and drought. In 1957, the Monticello Dam, pictured here, was completed, forming what we now know as Lake Berryessa. This, in conjunction with another small dam below Lake Solano, resulted in low flows. Eventually, this, coupled with drought, caused sections of the creek to run dry in some years, which resulted in the loss of anadromous fish populations. As with most things in the natural world, these changes caused ripple effects. The shift in flow created altered habitats that were more suitable for non-native species of plants, fish, and amphibians, as opposed to salmon. Later, a few wet years showed that recovery of fishes was possible with more water. Thankfully, a group of persistent citizens pushed for more water in the creek and worked with the water agency through the legal system in the 1990s to sign the Putah Creek Accord in 2000. This dictated the use of a natural flow regime to create seasonal flow for lower Putah Creek and to assess annually if and how native fish were responding to the new flow regime. And that's where we come in. But what do I mean when I say a natural flow regime? Well, I'll tell you. The Accord addresses, in part, flow requirements for the creek, prescribing not only minimum water flows to keep the creek wetted, but strategic flow patterns. The pattern of flow is designed to mimic how the creek would have worked prior to dam construction and regulation. The blue line here is what the hydrograph of a happy, healthy creek might look like. As time goes on the x-axis, the height indicates how much water is in the creek at any given time. You can see peaks and valleys in the blue line, and these would have been periods of high runoff from rain events or melting snow in some cases. Fishes that evolved to live in oscillating environments like this developed strategies to help them survive, like laying eggs when flow and temperature were adequate for their offspring, or timing migrations when there was enough water to help push them along. However, when a dam is constructed and flow in the creek becomes regulated, these peaks and valleys can disappear, and suddenly a fish's life history might no longer make sense. This is when the concept of a functional flow regime comes into play. If we can identify which flow patterns are most important, water releases can be timed to mimic them. This is demonstrated by the red line here. With the red line, we can see some of these mimicked pulses. First, in the fall, we can see a smaller pulse that might possibly be used as a tool to attract up-migrating salmon. And then we see peak flow in the winter time, and that might be important for shaping the riverbed. And finally, there's a late spring pulse, which perhaps might be used to help juvenile fish move downstream. And this is the type of natural or functional flow regime Peter Moyle really helped to formulate for Putah Creek. In addition to providing water at specific times of the year, there's been a lot of other work done to make the creek more attractive for salmon and other fish. The creek bed itself has been remodeled to remove a lot of the deep, slow pools left over from gravel mining days, and to replace these unnatural shapes with more of a riffle pool pattern. And that's what I've tried to show you here in this picture on the right. We can see kind of what a riffle would look like in the foreground, and then further back, it leads to a pool. In addition, a few years ago, the Water Agency worked to break up some of that gravel compaction and sedimentation that built up on the creek bed over the years. So if you can imagine one of those patios that has all the little pebbles embedded into the cement, that's kind of what the bottom of the creek had come to look like in many places. But salmon need loose, clean gravels to make their redds, lay their eggs, and protect their hatchlings. So the Water Agency helped to break that patio up and expose the good spawning gravels hidden below it. So after mitigation and restoration efforts and a return to a more natural flow pattern, favorable for various fish populations, the creek is wetted year-round and there's variation in flow now. So you'd be asking yourself at this point, like, okay, Mackenzie, that's great, but why does it matter? Why do I care? And it's because salmon are anadromous, meaning that they spend various parts of their lives in freshwater and saltwater. Adults return from the ocean to their natal streams, or the streams they were born in, to spawn. Eggs hatch in the gravel of freshwater, and they grow from alevins to par, or alevins to fry to par, and then to smolts before migrating to the ocean, where they'll spend 2 to 4 years growing before they come back. And to do this, they rely on environmental variability and the cues associated with that variability to tell them, like, okay, time to move on, or it's time to go home. So through their life cycle, they're really tying our oceans to our mountains, connecting habitats across our landscapes. Their lives are truly characterized by change. And I suppose that's reason enough to find salmon awe-inspiring. But why specifically is Putah Creek really important when we tell the story of salmon? Because only half of all of California's native trout and salmon run the risk of extinction in the next couple decades. I've included here a picture from a report that was written by UC Davis Center for Water Sedge Sciences, as well as Cal Trout, that further details the status of our native trout and salmon. So if you're interested, I've included that link here. And a large part of that threat that I just mentioned is due to habitat loss. Salmon combat many obstacles, but habitat loss for many reasons is among the most prevalent. Here you can see in all the blue lines some of the waters in California that would have been historically accessible to salmon. And here in the black, we can see just how much of that historic habitat is now lost to salmon. Habitat loss continues to threaten salmon survival globally, but through some of the work that's being done on Putah Creek, we can begin to see how one day we might be able to open those gates again, those waters for salmon again, just as once Putah Creek was inaccessible to salmon, but now provides new opportunities and new habitats. And it is, they're coming back, they're using this new habitat. And since roughly 2014, we've seen an increasing and returning adults to Putah Creek. Now, for many reasons, these numbers may vary, and that's something we're looking into as we study salmon. Numbers for 2019 look a little bleak here, and we did have very few adults who were able to make the journey upstream. And this is likely due to a passage barrier at the entrance of the creek, which is something I can talk more about later. Okay, so background covered, let's really dive into the meat of this talk and some of the ways that we're able to study salmon. There are lots of ways to learn about what a population is doing, all by looking at the various life stages of a salmon. Questions we may ask ourselves are, how many are coming back? Where are they coming from? Are they healthy? And are they surviving the migration to the ocean? So studying this becomes quite interdisciplinary. The work involves multiple labs at UC Davis working on microchemistry, genetics, biotelemetry, and ecology, just to name a few. So now I'll take you through some of the study tools we use to do this, and I'll start with carcass surveys. Carcass surveys have been conducted annually since 2016. These surveys are performed via canoe to avoid disturbing any redds. while also providing a good vantage point for us to see spawning salmon. We float the creek weekly while adults are present in the system. As we come across the carcasses, if we can guess that they originally came from a hatchery, we'll send the head to CDFW in Sacramento so they can verify if it's a hatchery origin fish or not. We sample a proportion of all fish spawning in Putah Creek by marking which carcasses we've sampled using a little tag that we leave with the carcass. And then on later surveys, we can note those fish with tags and can then estimate through mark recapture methods how many total spawners are in the creek. So as I just stated, sometimes while performing the surveys, we'll send some fish heads to Sacramento, which I know sounds super weird, but we're able to guess that these fish are of hatchery origin if they're missing an adipose fin. So pictured here is just a fish with an adipose fin and a fish without one, and it's just a fatty little fin towards the back of the fish. So once we've sent the heads to CDFW, scientists can find and remove what are called coded wire tags if they're present in the snout of a fish. And a coded wire tag pictured here in the bottom left is a teeny tiny embedded wire with a serial number on it. And it tells us where the salmon is from, how old it is, and where it was released. Adipose clipping and coded wire tagging is the standard way of marking a fish of hatchery origin. Currently in the Central Valley, 25% of all fall run Chinook salmon released from hatcheries are tagged in this way before they leave. I'd like to direct you first to this little plot on the right, where you can see that a majority of the hatchery origin fish we've come across in Putah Creek are from the McCulmy River fish installation. And strays in this context really just means salmon that have got lost on their way home, meaning that they didn't return to the creek that they came from originally. And as I said earlier, salmon use cues in their environments to find their way back to the rivers and streams they spent time in as juveniles. This is called natal homing. And sometimes the cues can get muddled and it can be really hard for salmon to find their way home. So McCulmy strays are just fish who would normally go back to the McCulmy River, but instead made a new home in Putah Creek. So we have a way to trace hatchery fish, but we can also track our wild fish. And my friend Malta will be better able to explain just what that means.
All right, well, thanks so much, Mackenzie. Let's see if this works. Yeah, it does. Okay, so before I get started with the fish ear bone otoliths part of this talk, I quickly want to go back to carcass surveys. And Mackenzie already mentioned those, so we float the river by canoe. And as you can see here, it's a really beautiful part of being a scientist. I mean, I got the chance to go out there a few times and I really enjoyed it. It's probably part of my favorite field work. And what you don't see on this image, though, of course, is that you're sharing your canoe with a bunch of dead salmon. So as we float down the river, we collect carcasses to then extract the otoliths. And you can see some of these fish are pretty decomposed. It gets tricky sometimes to identify if they're male or female, or even just measure the length. And I don't want to dwell on these slides for too long, but one really, I think, interesting aspect of this is that this ear bone, the otolith, this tiny, tiny structure you can see here, calcium carbonate, that we extract from this huge fish, it tells us so much about its life history. So it's kind of remarkable that we can get all this information about the fish just from this tiny structure inside its head. So salmon use their ear stones very much like we use our otoconia, which are like the small calcium carbonate structures we have inside our own ears. In comparison to us, though, in fish, these are like one single, basically a rock, and they use them for hearing and balance. And you can see another example here. So they're pretty small compared to the fish, but they are pretty big compared to other otoliths. So fish use those for balance and hearing, but we can use them for a whole different suite of applications. For example, the shape of the otolith or earstone can tell us about what kind of fish species we have. We can look at the individual rings inside the otolith and learn something about the age of the fish. So every day, another ring is deposited, and kind of like you would look at tree rings, you can do the same with otoliths and learn about their age. Looking at how wide those rings are, we can look at the growth, basically reconstruct phases of good fish growth versus poor growth conditions. And then finally, we can analyze those rings and actually look at the geochemical composition and relate that to the environmental parameters. So we can learn something about where fish have been. And just zooming in here, this is a juvenile Chinook salmon from Putah Creek. And you can see here the structure, which is the core. So this was already present when the fish spawned. And then as we go out, you can see all these rings, each of these rings representing daily growth. And so as we look at this, we can learn about, as I said, about the age of the fish. And so if we zoom out and we look at older fish, some of these daily rings get a little bit trickier to see, but we can see very distinctive marks. We can see when the fish hatched, we can see when it started feeding, when it entered the ocean, and when it completed years. So H1, H2, H3, H4, we can use this to figure out the age composition of this Chinook salmon that returned to Putah Creek. And here are some results from 2016. And you can see that most of the fish were 2 or 3 year olds, and only very few 4-year-old fish returned. Now, this is pretty typical for 4-run Chinook salmon in California. Chinook salmon along the Pacific are normally 3 to 4, maybe 5 years old. But here in the Central Valley, our age composition has been shifted to younger ages. And the reason this is really important is because, of course, age is also related to size. So 2-year-old fish are quite a lot smaller than 3-year-old or 4-year-old fish. And a smaller fish brings back less marine nutrients, probably lays less eggs. And so for the salmon population as a whole, this is a little bit of a problem. But Putah Creek is here right in the ballpark what we would expect for the Central Valley. Let's go back to the slide. Apologies for that. Let's try this. Okay, so we looked at ages and growth. The other part we can look at are geochemical tracers. And there's a whole range of different methods we could apply. We decided to use strontium isotope ratios. So the element strontium has multiple isotopes, and those ratios are directly related to the geology. And on the right here, you can see a geologic map of California, all the different colors representing different geologic units, and in turn, different strontium isotope ratios. And from the geology, this ratio is transferred into the watershed, and that means different water catchments have different strontium isotope ratios. And that means fish that use those catchments also have different strontium isotope ratios inside their otoliths. And so we can look at this, and we can use the facilities we have at UC Davis, and there's a machine called a laser ablation system. And we can use that instrument to basically run a laser across the entire length of the otolith, meaning we can look at the entire life history. Remembering that the core, so the center, is when the fish was born, and the edges on both sides is when this fish died in Putah Creek. And this is what a profile like this would look like. We have a core part relating to here, then the life and death. We take a statistical approach. We use a couple different methods to look at this, but we can basically distinguish the core, the natal portion, so the time the fish spent in freshwater, their adult life, so multiple years in the ocean, and the time they return to Putah Creek. So if we look at the core in this example, we can see that that line is kind of shifted towards the ocean signature. That means that these eggs were formed when the mother was still in the ocean. And that's really typical of California fall run. So just by looking at this profile, we already know that this was a fall run Chinook salmon. We can then look at the natal area down here and take that value and look at our map of different streams in California. And a lot of people have gone out and characterized these streams. So we can use the value we see in this part of the otolith profile and directly relate it to a specific geographic region. In this case, this fish was a Feather River hatchery fish. We can then look at the adult habitat. So we see that's multiple years in the ocean. That's really what we expect for Chinook salmon. But you could imagine some other fish might return to freshwater multiple times. Some other Chinook salmon in other systems, for example, in Alaska or Washington, actually spend longer time in freshwater and don't transition immediately to the ocean before year one as our fall run. So we did this for the Chinook salmon returning in 2016. And similar what we saw with the coded wire text, we found that most of them, 88%, were of hatchery origin. We saw that a lot of them came from the McCallum River fish hatchery, but also from the Feather River fish hatchery, from the Coleman National Hatchery, so that's between Red Bluff and Redding, or the American River Nimbus fish hatchery. We also saw that 3 of them were wild fish, so that's pretty encouraging, even though it's a small number. Given how many hatchery fish in our fall run there are in California, that's actually pretty okay. 2 of them came from the McCallum River, and 1 fish was really interesting because it either comes from the Feather River, so not from the hatchery, but actually the Feather River, or from Putah Creek. Sadly, our geochemical tools weren't quite good enough to make this distinction. There's a lot more Feather River fish than there are Putah Creek fish. But it is encouraging that some wild fish returned. And then there were also a few fish, about 9%, where we couldn't quite sure if they were of hatchery or wild origin. That's just related to the uncertainty in our methods and something that we hope that will go down as we continue working on this. And so to just sum up the otolith part of this talk, we saw that most Chinook salmon that returned to Putah Creek in 2016 were 2 to 3 years old. They came from at least different natal sources, mainly from Central Valley hatcheries, but also from the McCallum River and maybe the Feather River. And if we think about it, there is really no natal homing for those first years in Putah Creek. Fish had to stray from somewhere. We didn't have salmon here before. And that they're coming from 7 different sources, that's pretty encouraging. Even though genetically, Forerunner are pretty homogeneous throughout the Central Valley, at least we are capturing what remaining variability there is. And so as we move forward and we will work on multiple years, we will see if this Putah Creek Chinook salmon, if those numbers start to tick up and those straying fish, if that numbers goes down, or if we have to implement any types of management actions. And I think that's enough from me. I'm gonna hand it over to Gabe, and he's gonna start talking about the juvenile salmon.
Okay, let's see.
I think I'm next, actually, Gabe.
Okay, all right, go ahead.
First, Malta, thank you for sharing that. That's a lot of that was new information for me. Okay, so now we've talked about adults and what kind of information we can get from them. Let's talk about this fry stage or the par stage next. This slide not only shows our rotary screw trap, which is how we catch juveniles as they outmigrate, but it also shows our capture rates in 2017, 18, and 19. And really quickly here, it's important to note that the numbers of fish varied a lot over these years. In 2018, we caught nearly 33,000 juveniles. But in 2017 and 2019, we caught much fewer. And this can be a little scary, like if you think, well, why are numbers dropping? But this isn't necessarily a reason to panic. This discrepancy is more likely caused by changes in our sampling window than a drop in the population. In 2017 and 2019, Putah Creek experienced really high flows, and in a lot of places it flooded. And when the water is high with significant velocity, we're not able to operate the trap safely for extended periods of time, the same way we did in 2018. And I've included this picture here just to show why sometimes we can't fish our trap as often or as consistently as we would like. But back to the data, here in 2018, highlighted in the red box, you can see how even a smaller pulse flow event, that little uptick in the orange line, can increase our capture rate. And whether that was caused by rain or dam discharge, that increase in flow, I couldn't tell you for sure. And this caused us to catch greater juvenile fish as more water moved downstream, carrying with it more juveniles. And so smolts is this stage in salmon life history where they're physiologically preparing to live in salt water. So again, in this stage, they'll follow environmental cues like flow and temperature to outmigrate. And that's why it's so important to have kind of this natural flow regime, because they evolved to live in a dynamic environment and rely on the variability to tell them when to do something. And I don't have the 2020 data pictured here, but despite some of the COVID craziness, we were able to capture 200 juvenile Chinook salmon just in April and May, which was pretty encouraging because, as I said earlier, we saw really very few adults return to the creek this year. So we still have a lot to learn about the reproductive success in Putah Creek, but the fact that we've captured juveniles over the past 4 years indicates that adults are spawning successfully. And this plot here on the right I have is supposed to show you that their kids are doing okay. The plot displays condition factors of all juveniles caught in Putah Creek for the last 4 years. And a condition factor is a metric used to assess the relative health of a fish by essentially comparing its expected size to its actual size. And a condition factor of 1 is considered a plump fish. So given this data, the juveniles in Putah Creek are faring fairly well. The average condition factors in all years is greater than 1, indicating that there's presumably an abundance of food to support their growth and development. And this just means that our salmon are growing into chunky little footballs. And this picture on the left is one of our chunky footballs. So in the spring when we're sampling with that rotary screw trap that I just showed you, we catch a lot of other fish too, not just juveniles. And these are some of the species that we might capture. There's a lot of non-native fish in Putah Creek, but also a lot of native fish like suckers and pike minnow and lamprey, just to name a few. And some of them are pictured here. On the left is a lamprey, which, like salmon, spend various parts of their life in saltwater versus freshwater. And then in the bottom middle is a tule perch. That's a native fish. The top right is a largemouth bass. It's non-native. And then in the bottom corner, we have a crappie, which is also a non-native fish. Okay, so we briefly talked about juveniles and we talked about adults. Now let's talk about smolts. And as I said before, smolts is that life stage that's getting ready to move to the ocean. So like a little bit like 18-year-olds getting ready to move out of the house and into the dorms. And my friend and colleague Gabe will be better able to explain to you how we can track these guys as they move on to the ocean.
Really quickly, can I pop in just really quick? I forgot to mention at the very beginning, if anyone has any questions, go ahead and pop them into the chat box and we'll try and be as specific as possible and we'll answer them at the very, very end. Okay, thank you. All right, go ahead.
All right, let's see if this works. Okay, there we go. Oh. So I'm going to briefly talk about how we address some of the challenges of tracking small fish in environments where they're difficult to directly observe. I'm going to touch on the methodology and the tools that we use, and then hand it back to Mackenzie to talk about some results. She also briefly mentioned some of the methodology earlier when she was talking about the carcass survey, and mark recapture is a really broad tool that you can use for a lot of different things. And so that's kind of the main methodology that we use here. And then the tools are acoustic telemetry. And I'll talk about that in a second here. And so basically we're combining new technology with kind of tried and true mark recapture methods to track these fish as they leave Putah Creek and head towards the ocean. So I'm going to run through mark recapture in like 1 minute and give a quick lesson on that. In its simplest form, mark recapture methods give us a way to estimate the abundance of a closed population. And when I say a closed population, I mean that fish don't enter or leave the population during the study. So say we have a body of water, we want to know how many fish are in there. But we can't, the water's murky. We can't go out there and just observe and look and count them. So we're going to do some sampling, and we're going to use mark recapture methods. So we go out there on day 1, and we do some sampling, and we catch 10 fish, and we mark them all. And that's on. Oh, let me move forward through the slides here. So we catch 10 fish, and we mark them all. That's day 1. There's our little fish with their little marks on them. That N sub 1 on the left-hand side there, that's the number that we caught day 1 and marked. That mark could be a fin clip, like the adipose fin that Mackenzie mentioned. It could be a Floy tag, like they put in the carcasses, which is like a visible kind of, some people call them spaghetti tags. So that's our marked population. And that marked population is some proportion of the entire population, that capital N. So we mark these fish, we let them go. Am I frozen? Can you guys still hear me? Yeah, okay. We let them go, they disperse into the greater population, and then we go back on day 2. And we do some more sampling. And on day 2, we catch another 10 fish, and of those 10 fish, 5 are marked. So that's our M sub 2, and then the N2 is the number that we caught on day 2. Now, if those marked fish that we caught on day 1 have dispersed evenly throughout the population, then the marked proportion in the whole population should be equal to that marked proportion in our sample population on day 2. And so through our sampling, we have 3 of these 4 numbers that we need to make our estimate of population size. And we can rearrange our equation and substitute in the numbers from our sampling, and we arrive at an estimate of 20 fish in our population. So there are a lot of extensions of this basic methodology, and they can be used to derive estimates of not only abundance, but births, deaths, immigration, emigration, and more. And in the case of juvenile salmon in Putah Creek, we use a version of these methods to track our marked fish through space and time as they leave the river. By following this same group of marked fish, and by following the same group of marked fish, we can determine their survival as they migrate down the river and the probability of detecting these fish at each one of our receiver arrays. And if they're routing through, if there are multiple pathways from point A to point B, we can also determine their routing. These methods also give us the ability to add covariate data to our statistical models so that we can test hypotheses like whether larger fish tend to have more successful migrations than smaller ones, or whether release strategies impact survival. So the form of marking or tagging that we do in this case is generally known as telemetry. And telemetry just means the transmission of data as opposed to archival technology, something like that, where data would be stored on the tag and you would have to retrieve the tag to download it. Telemetry allows us to mark one fish one time and then recapture them many times with the receivers without an additional physical handling event. And this is a huge advantage when you want to collect information on hard to see organisms or organisms that are engaging in an active migration that you don't want to interrupt any more than you already have. Telemetry comes in several different forms. There's active telemetry and there's passive telemetry. Passive telemetry typically refers to pit tagging technology. That's on the two photos on the left there. Where the tags are very small, they have no battery in them. And so they must pass really close to an antenna to be read. And then you have active telemetry, which employs transmitters that are powered by batteries, which extends their detection range, but also can limit their life. Within acoustic telemetry, within active telemetry, there are two main types. There's acoustic and there's radio. Radio telemetry uses electromagnetic waves to transmit a signal, and acoustic telemetry uses sound waves to transmit a signal. Here we use acoustic telemetry because it functions better in a variety of aquatic habitats, allowing us to track fish in shallow rivers, through the delta, into the estuary, and all the way to the Pacific Ocean. And just for fun, I threw this in here. This is, so you can see the next generation of acoustic transmitters that are currently in development. Folks at Pacific Northwest National Labs are working on an acoustic transmitter that's powered by energy harvested from the fish that you implant them in. So presumably, as long as the fish is alive and moving, the tag will be powered. So it would extend the life similar to that of a pit tag, but you would also have the advantage of the extended detection range that you have with acoustic tags. So I'm going to talk a little bit about how the transmitters work. There are different ways that acoustic signals are transmitted and decoded. The first way is by pulse train, where the timing between the pulses of sound emitted by a transmitter are decoded by the receiver to give you the unique ID code of the fish that's tagged. First, the transmitter will send a sync pulse out to the receiver, and that sync pulse just says, hey, wake up, I'm about to transmit my ID code, here it comes. That's followed by the fish's ID code. And then lastly, there's some error checking, that checksum value that you see at the bottom. There's usually, with this kind of tag, there's some kind of delay between pulse trains. That delay usually varies a little bit so that you don't have two tags that you turn on at the same time that constantly walk on each other, interrupting the transmission of their code. This method of transmitting an ID code can take several seconds to transmit the entire code, which can cause problems if there are a lot of tagged fish in a small area. Trying to transmit their codes at the same time, they will walk on each other and prevent the receiver from recording a detection. So luckily, we have other methods of transmitting acoustic signals. The transmitters that we use on Putah Creek employ this binary phase shift keying method of transmitting their ID code. And with this method, they can transmit their ID code in fractions of a second. And so basically what happens is the transmitter sends out a carrier signal. That carrier signal is modulated by the chip on the tag. between a 1 and a 0, and it produces a 31-digit binary string of 1s and 0s that get decoded by the receiver into a 4-digit hexadecimal ID code, and that just means a combination of letters and numbers. So the transmitters get implanted into the abdominal cavity of the fish through a small incision made on their ventral side. This series of photos, starting in the upper left, kind of walks you through that process. First, the anesthetized fish are measured, and then we make a small incision in that center photo near their midline. The disinfected transmitter in the upper right is then inserted through the incision, and then the incision is sutured closed in the lower right. And then the fish are held for observation until they're recovered, after which they're released into the river. So the other important part of the telemetry system, kind of mentioned it already, is the receiver. And that records the dates and times of detections of our individually tagged fish. These also come in many different forms. Some are deployed and have to be retrieved and downloaded, like the one on the bottom left photo. And others are equipped with cellular modems and can give us near real-time detection information without having to leave the office, like the setup that's being installed in the upper left photo. Receivers are spaced to ensure that migrating fish are not missed as they pass through our detection arrays. And so in the center, you can see a diagram of how we might approach different deployment scenarios. So kind of in the top in the center where it says River Y, in a small stream, we might deploy a single receiver, whereas in a wide estuary, we might deploy a line of about 10 receivers. The spacing will be determined by range testing, so we'll have an idea of how our detection range is in different environments and then make a deployment decision based on that. One more quick side note about this technology, and this isn't something that's done in Putah Creek, but we do this in other areas in the Central Valley. You can deploy a very dense array of these acoustic receivers in a small location, and then you can use them to triangulate a 2D or 3D position of a tagged fish. So you can get 2D and 3D movements of fish in small areas using this technology, which is pretty neat. So here's a quick look at what the array looks like in Putah Creek with 7 receiver locations covering the stretch of creek downstream from Winters. And you see the initial capture point marked with the star there. This also feeds into a broader array of receivers in the Central Valley that are maintained by a large group of state and federal agencies and universities and environmental consultants. Everybody kind of gets together to coordinate our resources and make these studies as efficient as possible. Now for the scary part. After the fish swim through the receiver array, the data is downloaded, and then we recreate the path of the fish using a string of 1s and 0s, depending on if the fish was detected at a receiver or not. We call this the capture history. Here's a simplified example on the left. You see all the different capture, all the different capture histories. Each one of those possible capture histories can then be translated into a probability equation. Then we combine the equations and we weight them by how often that capture history shows up in our data. We throw some more scary math at it, and we get back the most likely estimates of survival between each receiver array and the detection probability at each receiver array. And then if there are multiple pathways from point A to point B, we also get estimates of the proportion of the population that chose each pathway. So that wraps up your crash course in telemetry and mark recapture methods. I'm going to hand it back to Mackenzie now for the rest of the presentation.
Awesome. Thank you, Gabe, for explaining the intricacies of telemetry and the scary math, because a lot of it still eludes me. Okay, so I'm going to direct you all to this graph on the right. And this is essentially when Gabe was talking about, I was going to share some results with you all. That's this. And this just shows a number of the fish we tagged in 2019 leaving Putah Creek. So each line that makes it to that red exiting Putah Creek line at the bottom indicates that a fish made it over the flashboards. And it wasn't a lot, but it's kind of like proof of concept. It can be done. And then I included this picture on the left to show just how far some of our fish have to go to make it to the ocean. And that really poorly read drawn line, that's the path they would have to take. So the picture here on the left is the check dam and the flashboards that I was just referring to. And this is essentially the gate to Putah Creek. These boards are removed seasonally, and they're removed in late October, which we are rapidly approaching, and replaced in May. And fish can't move upstream while they're in, and it's unlikely that many make it out while they're in, although, again, we did see a few make it over those boards in 2019. And then this other picture I have here on the right is the very tail end of Putah Creek. And I took this picture standing on the check dam. And I just put this in here to show you that parts of the creek, this is how the fish are going to access Putah Creek. And it can be shallow and warm and really channelized. And this is what eventually connects Putah Creek to the tow drain, which then connects to the Sacramento River, to the Delta, onto the ocean. So this year, with the collection of adults in the fall and the genetic samples we collect when we do those carcass surveys, might be the first year that we can link families in Putah Creek by a method called parentage-based tagging. So we'll be comparing genetics from adults collected a couple years ago to the genetics we collect this year, hopefully identifying some family lineages. And this may give us an indication as to whether or not a self-sustaining run of naturally spawning salmon is on its way to reestablishing itself in Putah Creek, and not solely composed of hatchery strays or strays from other rivers. So aside from the science that's being done, what can we as citizens do to be more fish friendly? The Davis Winters community has already taken a lot of steps to be fish friendly, and the community participation is really critical. Some of the other ideas that Gabe Malta and I brainstormed for things we can all do is, number one, remember that we share the creek with salmon. And sometimes that can mean keeping ourselves and our pets out of the creek when we know adults are present in the system, so that we're not disturbing them, so that we're not harming them, and so that we're not crushing their redds, which would be harmful to the eggs beneath. Additionally, we can continue to educate ourselves and our communities through programs like trout, steelhead, and salmon in the classroom. Through this program run by CDFW, biologists bring little tanks of eggs into the classroom, and students can really be a part of the hatching process, watching these fish grow up. And it's a really great way to inspire kids and continue to foster stewardship. And as always, we can try to keep the creek in good condition by keeping our trash out of it and being aware of sensitive habitats. And a quick plug for the Winter Salmon Festival, which unfortunately isn't happening this year, but it's a really great way to connect with the community and share not only the science we do and the monitoring that we do, but a lot of other organizations are usually there. So in summation, there are many efforts underway to improve access to Putah Creek, restore habitat, and better understand the what, where, and when of Putah Creek salmon. Putah Creek continues to provide us with a really neat opportunity to study the reestablishment of salmon under new environmental conditions as well as in an urban landscape. And before I'm totally done talking, I'd like to acknowledge our collaborators, fishy friends, and my fellow presenters, Gabe and Malta, who really took on a brunt of this presentation in explaining some of the more complex ideas. This is a really interdisciplinary project, and it takes a lot of scientists and community members to make it happen. Our research is supported by the Solano County Water Agency and the folks there, as well as our really, really amazing team at UC Davis and CDFW. We have a lot of excellent, really passionate biologists that really pull the project together. And I think with that, Gabe, Malta, and I might be able to field any questions you have. Thank you, everybody, for listening.
Awesome. Thank you all. Thank you both, or all three of you, so much. That was wonderful, very informative, very exciting. Definitely going to have to watch the telemetry part again. I have to rewatch that, but really awesome. So we've got 2 questions, and I figure the way that we'll just read the questions, and then whoever is directed to or whoever can best answer it, or if it's all 3 of you, that's really fine. So our first question is from Kelly Neal. She said, are you sampling macroinvertebrates or looking at the gut ID of some of the juveniles to see what they are eating?
So at this time, we're not really looking at the macroinvertebrate population in Putah Creek, but every year we're adding new parts to the project. This year, I think we're adding 2 or 3 new parts. So it's likely that in the future, something like that would be possible.
Awesome. And then we've got another question from Sonia. How does excessive winter flooding of the creek affect salmon? So in a flow year, like was it last year or 2 years ago? Yeah.
Yeah. So I can start on this one, but I'll imagine Gabe and Malta might have some things to say as well. So in a big flood year, it can do a lot of things for salmon, some good, some bad. It can help move juvenile salmon downstream, which is good because we eventually want them to leave the system. But we also don't want it to push them around too much, which it can sometimes do, which is in part why habitat complexity is really important, because if you have kind of a diverse habitat, you have areas where flow isn't as strong. And so it provides some refugia for those juveniles, because too much flow might be a little ouchy.
Yeah, just to add to that, I think in 2017, when it's a massive flood year, and it looked like salmon in Putah Creek actually did fine, but our scientific monitoring was really impeded. Like we couldn't actually monitor any of those floodwaters. And that wasn't just a problem for Putah Creek, that's actually happened across the whole system. In 2017, most of the surveys didn't catch many fish, even though we know they probably actually did pretty well.
Yeah, I think that's right. I think it's probably all right for the fish. I think that one risk in Putah Creek is stranding when it floods a little bit like that. There are some places in the upper reaches where when they flood and it recedes, fish get trapped. We did do some sampling. Emily would know more about that if she gets a chance to answer some questions about it. But I think as far as the salmon go, you know, Putah Creek is small. You saw the photo that Mackenzie showed of the kind of last stretch before it dumps into the tow drain. That does not look like your typical salmon habitat. So more water in there is probably good for these fish.
Awesome, thank you. We are getting a flood of questions. So from Dan, has there been any study of the spawning habitat or red quality over time?
So we don't directly survey the habitat necessarily, but a few years ago they did kind of kick up and kind of till the bottom of the creek to improve what would be the spawning habitat. So by loosening those gravels, the adults can come in and better create reds. I'm gonna have to read some of these questions.
Thank you. And then from Andrew, is the diversion dam the upstream limit for the salmon?
Yes.
Yeah.
They can't get, there's no passage beyond that. So the diversion dam right at the base of Lake Solano is the uppermost limit for anadromous fish populations.
Thank you. And then from Leslie, what kind of mitigation is being done to prevent excess sedimentation due to the LNU fire?
I really don't know the answer to that question yet. I know that there are some local groups who are interested in being involved in that. But as of right now, I don't know what's being done at the moment.
Okay, yeah, it's kind of soon to.
Yeah.
And then from Corey, do any of these projects share, exchange, or collaborate with the local indigenous communities?
Not to my knowledge, not this project specifically, not the work I do. There are other people in our lab who do work like that, but I can't really speak to that.
Okay, thank you.
I can only add that that would really be a really interesting next steps that we should take. Yeah, I think there could be a lot learned from that perspective.
Absolutely. And then one last question from Janet. Do the egrets and herons that hang out along the creek eat the smolts?
I would say it's very possible. Have I seen it with my own eyes? No. But I think I've seen egrets and herons eat other fish. So I wouldn't say it's out of the realm of possibilities.
I agree. I think it's likely, but I haven't seen it myself either. I know that in some river systems, they end up finding a lot of the either pit tags or acoustic tags like in little bird colonies. So I would say it's likely.
Awesome. Okay, well, thank you so much. That was the last of the questions. I just want to say thank you to you all for sharing the evening with us and for participating in this program. It's one of our favorite programs here. So it's awesome that even during these strange times, we're still able to share it with a large group. And thank you so much for donating your time to this. It was really awesome.
Yeah, we're happy to. Thank you very much for hosting us tonight.
Yeah, thanks for inviting us.
Thank you for having us.
If we were in a normal room, you'd get a round of applause right now, but everyone's mic is off. Thank you so much. Bye, everyone. Thank you.